All right. Good afternoon, everyone. Good morning to those of you that are over on the West Coast. It's still morning for you. It looks like for the rest of us, we're into the afternoon session. As Michelle already indicated, my name is Jim Smith. I'm with the American Wood Council. I'm the Midwest Regional Manager, and I'll be your presenter for today's webinar. And it's on an introduction to mass timber products. It's the AWC course designation is indicated there on the screen, is DES 620, and this is it's really an intro type of a session. So we'll touch on a lot of good stuff, like a 101 course on what all of these different products are. We can bounce by this one. Cheryl already covered that. Here's our AIA slide, basically to let you know that this is this course has been registered with AIA CES for continuing professional education. And the next we have the copyright slide. Basically this one, it's the standard slide that we put up. In this case, it's a little bit different than our normal slide because the copyright are held by both the American Wood Council and the International Code Council. A little bit of information on the background for this this series, if you will. AWC already, or ICC has already presented these. They've actually done a series of 6 webinars on the very same subjects that we'll be covering in our webinar series. We're only going to be covering 5 of the 6 segments, but we'll get you a little bit more information on that later. But again, this was a joint effort, and I'm hoping you'll enjoy the presentation. Description of the presentation. Well, hopefully this should match up with the description you read when signing up for the webinar. So there shouldn't be anything new in there. It's going to cover a lot of good information for you. And hopefully after you're done with the presentation, or at least I'm hoping that I'm able to provide you with the information so that when you're finished, you can identify the acceptance criteria that's found in the IBC for the various mass timber products, that you can describe the technology advances and standards related to mass timber products. You'll be able to recognize mass timber's unique fire resistance characteristics that influence their use, and that you'll be able to describe what NDS Chapter 16 can be, that it can be used for the design of exposed wood for up to 2 hours of fire resistance. This shows you the modules. Again, these are the 6 modules that ICC that we put on in conjunction with American Wood Council. In fact, for these modules that I have listed there, in almost every one of those cases, the majority of the presenting was done by AWC staff. So you're going to have a lot of the same information as we move down through there. You'll notice down by Module 5, AWC doesn't plan to present that part, that Module 5, which is Part 3 of the basic information related to the 2021 IBC. But things have been shifted around a little bit, and all of the information, we plan on covering all of the information. I'd like you to be able to think of this as this very first presentation, my presentation, as Mass Timber 101. Some of the basics will lightly touch on subjects that will be covered in far greater detail in the upcoming modules. These are the teasers, if you will. So with that, sit back, enjoy yourself, and hopefully use the chat box to submit any questions that you might have. We'll try our best to get you answers as we get to the end. And of course, we're going to try to keep you engaged. And you know, I'll with the tongue planted firmly in cheek, we have a number of polls embedded throughout. No no scorekeeping is involved, but with that, I'll move over to the first poll question for Michelle to handle.
Yep, and here we go, launching our first poll, which should be rather easy. What is your profession? A, architect, B, engineer, C, code official, D, fire service, and E, builder, manufacturer, and other. And unfortunately, we're limited for the amount of answers that we can provide. But if you're other, feel free to let us know in the question box also what other you are. And it looks like we have a good amount of replies, and I'll go ahead and close the poll and share it. So we have 10% architects, 63% engineers, 20% code officials, 2% fire service, and 6% builder, manufacturer, and other. And one person said their other is a building designer. And we want to thank all of you for joining us.
Now, even though, you know, I brought this slide up there, just basically, you're going to see a lot of information on the NDS. Even though I'll be pointing out to this standard many times over the course of this presentation, I thought it appropriate to note the standard referenced by the IBC for the design of wood construction is the NDS. The edition will vary based on the edition of the model code being used in your areas, but for the slides in this module, we will typically refer to the 2018 editions of the IBC and NDS. For far more detail on the changes that will lead up to the 2021 IBC provisions that are tied to tall wood, please join us for Module 2 in the series coming next month. That'll provide for you, as Michelle noted earlier, she's going to be covering the 2015 edition and the 2018 edition of the I-codes and the information that's included therein. And then as we move on to the third module, you'll start getting into some of the lead-ins to all of the information, all of the testing that was done, everything that led up to the code change proposals that ultimately make up the 2021 IBC provisions for tall wood. So please join us. I think you're going to find I hope you find my presentation informative, but I think, you know, for those of you that are, you know, starting to get more and more into the mass timber provisions and potentially the tall mass timber provisions, you're going to find the upcoming series of webinars very informative. This is a basic outline for the presentation. What I'm going to do is I'll start with an introduction to the various types of mass timber elements. I will then touch on each type of mass timber product by showing the acceptance criteria that's spelled out in the code for each type of product, the technology associated with each type of product. I'll include some examples of applications where those products have been used. And then at the very end of the presentation, I'm going to briefly, and I'll say briefly, it's very briefly, touch on the basic concepts of fire resistance design for the mass timber elements, hopefully to get you thinking about how inherently safe mass timber is when it comes to exposure to fire. Mass timber products, and again, there's all kinds of acronyms. I think this slide is pretty good. It's the alphabet soup. Mass timber is a term being used to describe wood products and built-up assemblies having large dimensions and mass. This is a list of those elements that can be considered mass timber, provided they're massive enough to be in compliance with the minimum size requirements spelled out in Chapter 6 of the IBC for Type 4 construction. As you go down the list, you will see the various acronyms that have been assigned to the different products over the years. Sawn lumber is commonly referred to as HT when it's of the right size. Glue laminated timber is glulam or GLT, depending upon the application. Mechanical laminated decking is referred to as NLT and DLT. NLT being nail laminated timber and DLT being dowel laminated timber. LVL, PSL, LSL, and OSL all fall under the category of structural composite lumber, as referenced within IBC section 602.4. Closing out the list are the newest products that are out there, cross-laminated timber, or CLT, and then mass plywood panels, or MPP. I included this slide just, if you sit back and think about what commonly pops into your mind when you think about wood construction. What you're seeing on the slides is pretty typical. It's conventional light frame, or commonly referred to as stick construction. That's not what we're talking about when we're dealing with mass timber. So you're going to want to see if you can start shifting a little bit and being open to the concept of wood construction not being light frame. So mass timber elements are not light frame. As you can see from the picture on the left, as compared to the conventional light frame or stick construction on the right. Totally different. Even though light frame wood construction is not going to be allowed for the new tall mass timber building provisions discussed in the upcoming webinars, it is important to remember that the mass timber elements, or that it's important to remember that mass timber elements that we're talking about can be utilized in all of the other types of construction by virtue of its mass or its ability to be fire retardant treated. So the mass timber is not going to be limited to the types of construction that are currently in Type 4 and the new types of construction that are in the 2021 edition of the IBC. Mass timber, is allowed for types 1B, 2, 3, and Type 5 for roof framing when the required fire resistance rating is 1 hour or less. You can find that specifically called out in footnote C in Table 601 of the code, which states that heavy timber roofs shall be allowed where a 1 hour or less fire resistance rating is required. Mass timber is allowed in Type 1A wherever FRT is permitted by Section 603.1, as well as for balconies and similar projections as permitted by IBC Section 705.2.3. Again, the future webinars in Module 3 through 6, or 3 through 5, have a lot more information about tall mass timber and the 3 new types of constructed being introduced in the 2021 edition of the IBC. Got a little bit of information down there on the bottom. That's it's types 4A, 4B, and 4C. And just a reminder that only mass timber elements can be used. If it's going to be combustible, it's got to be mass timber when you're dealing with those types of construction, those newer types of construction. As a sneak peek, again, one of the first of my sneak peeks into the details that will be provided in the future webinars, this slide is providing some general information on the minimum sizes necessary to be considered mass timber. The details are found in IBC sections 602.4 and 2304.11. Included within 2304.11 is a reference to table 2304.11 that is similar to that which I've shown on the slide here. So the first of the list, as you can see, we got that list, and we're going to try to go through and touch on each one of these for you with just a little bit of information. Starting off, we have sawn lumber. It's first on the list of those materials that can be a fit for mass timber, provided they are large enough dimension and mass. Effectively, any of the minimally sized wood elements that are massive enough to be classified as in compliance with the minimum size requirements spelled out in IBC Chapter 6, and for the Type 4 heavy timber construction to be considered mass timber. Basically, that slide, the previous slide where I showed the table of the minimum sizes, that'll give you a pretty good idea of what those minimum size requirements are. A little bit more on the details of the definitions for these terms a little bit later on, but whether beams and stringers or posts and timbers, the NDS defines them as having nominal 5-inch and greater dimensions. To be used in the IBC, sawn lumber must comply with the criteria found in DOC PS 20. It's the voluntary product standard for American softwood lumber. It's also spelled out. You can, if you want to see where that reference is in the IBC, you can find that in 2301.1.1. The NDS is the standard referenced by the IBC for the design of wood construction. Now, what I've shown on the slide here is the NDS plus the NDS supplement. The NDS supplement provides information like nominal sizes, section properties, and the design values that are plugged into the formulas that are found in the NDS. So when you're using the NDS supplement is really important to have available and to use, because the formulas in the NDS, to find out the information and where they plug in, you go to the NDS supplement to get that type of information. In the NDS, Chapter 4 is where you'll find the sawn lumber design category, the sawn lumber design provisions. In the supplement, you'll find all of that information in Chapter 4. The NDS supplement design values for wood construction. It's a separate document from the NDS, but it's where you'll find all of the details and formulas for the design of wood elements. But the values for many of the specifics called for in the formulas are found in the NDS supplement. Examples are section properties and design values for the various species of lumber. Going back to those definitions I told you I would touch on. In the NDS, in section 4, in 4.1.3.3, beams and stringers refer to lumber of rectangular cross section that are 5 inches nominal or more in thickness, with their width being more than 2 inches greater than their thickness. Grading is done with respect to its strength and bending when loaded on the narrow face. NDS 4.1.3.4, speaking to posts and timbers, refers to lumber of square or approximately square cross section. That is 5 inches by 5 inches nominal and larger, with width not more than 2 inches greater than thickness. And the grading is primarily for use as posts or columns carrying longitudinal load. As you can see, for the different sizes, some of the western species, the sizes that are out there, going all the way up to 20 by. Southern pine is typically going to be built up, and the lengths can be provided to you in 8 to 20 foot lengths, typically in 2 foot increments. NDS 4.1.5.2 says that indicates that for 4-inch nominal or thinner lumber, the net dry dress sizes are to be used in all computations of structural capacity, regardless of the moisture content at the time of the manufacture or use. NDS 4.1.5.3 indicates that for 5-inch, so these larger posts and timbers that we've been talking about, for 5-inch nominal and thicker lumber, the net green dress sizes are to be used in the computations of structural capacity, regardless of the moisture content at the time of manufacture or use. Hey, our second poll question.
Okay, I'll launch the poll. And the question is, in what chapter of the NDS will you find the design requirements for sawn lumber? And the options are A, Chapter 4, B, Chapter 6, C, Chapter 8, and D, Chapter 10. Okay, a little bit more for those that are still wanting to participate. Okay, so we'll close the poll and share the answer. In what chapter of the NDS will you find the design requirements for sawn lumber? 73% said chapter 4, A. 20% said B, chapter 6. 6% said chapter 8, C, and then 1% said chapter 10. And the right answer is?
The majority. Correct answer is A. Chapter 4 of the NDS is where you will find the design requirements for sawn lumber. Good job. Good job. Next up, we're going to jump into glue laminated timber. Glue laminated timber is the next on the list of those materials that can be a fit for mass timber when of large enough dimensions mass. What is glue laminated timber, or the commonly referred to glulam? It's a composite of lumber and adhesives that is routinely used for structural applications. You can find the IBC definition for structural glue laminated timber in section 202 of chapter 2 in the IBC. This is a picture. This kind of gives you an idea on the sizes and the scale of some of the larger glulam or the sizes of the elements that are out there. Columns on the left, and then over on the right-hand side, some very deep beams. So very, very large elements. They've been around for quite a long time. They're used in many, many different applications, and with the newer, taller mass timber buildings, you're finding oftentimes that the glulams are used as the main frame for the products like cross-laminated timber or nail-laminated timber. Some of the characteristics. In glulams, the grain of all lamination run parallel with the length of the member. Individual laminations are typically 1 3/8 inches thick for southern pine and 1 1/2 inch thick for western species, although other thicknesses may also be used. One of the most common widths for glulam is 5 1/2 inches, but of course glulam products typically will range in net widths from 2 1/2 inches to 10 3/4 inches, although virtually any width can be a custom product. Remember, to be classified as mass timber, the elements need to meet the width minimums, and the depth minimums specified for heavy timber. Here's, if you can remember when I showed the alphabet soup, you noticed, you probably remember that I referred to glulam and GLT. This is probably one of the lesser used applications for glue laminated timber, but if it's used as a panel, it's typically referred to as GLT rather than a glulam, which is the beams and columns. Under the code acceptance portion, IBC section 2303.1.3, that's the section that refers to ANSI A190.1. That's the standard for structural glue laminated timber. That establishes the nationally recognized requirements for the production, inspection, testing, and certification of structural glue laminated timber, and provides material suppliers, producers, distributors, and users with a basis for common understanding of the characteristics of this product. ASTM D3737, that's the standard for establishing the allowable properties for glulam. A190.1, the structural glue laminated timber represented to comply with the standard must be distinctively marked. Shown here is an older trademark of a glulam beam manufactured by APA members certified with the APA. To give you an idea on what the varying information refers to, if you take a look at the logo or look at the stamp, beginning at the bottom center and then proceeding clockwise, the laminating specification shows unbalanced, and that's the indicating the type of layup used for laminating. Available layup types include balanced, Balanced layups are used for continuous or cantilever span. No, they're balanced or used for simple span. Nope, continuous, I was right, balanced. Continuous or cantilevered span bending member. Compression tension lambs are the same grade. There is no top or bottom. Single grade, that's where the compression or tension, it's for use as a compression or tension only member. All of the laminations are of the same grade of lumber. Unbalanced, that's typically used for simple span bending members. Compression and tension laminations are different grades. There is a top and a bottom for installation. In fact, they're marked that way. The top of the element is marked top for installation so that we get it right. Continuing on, ARCH, that designates the appearance grade. Available appearance grades include industrial for enclosed or exposed areas where appearance is not important, architectural, as shown by this, which is for exposed applications, and then premium is a custom order where appearance is of prime importance. Framing is the last of the designation. That's enclosed for enclosed uses such as headers. The 24F-V4, that indicates the structural grade designation. In this case, the 24F indicates an allowable bending stress of 2400 psi. The V indicates visually graded lumber. If that was indicated as E, that would indicate that the lumber was mechanically graded lumber that was incorporated in the laminations. The wood species is the DF/L. And like I said, that's the wood species. And in this case, this glulam is made from Douglas fir larch laminations. And the last one is the applicable standard. And in this case, we're talking about ANSI A190.1 12 edition. In the NDS, Chapter 5 is where you'll find the glulam design provisions. And of course, moving over to the ever important NDS supplement, Chapter 4, you'll see that the NDS supplement, it's a separate book, and that provides the latest design values for glue laminated timber. This is a graphic or a number of pictures that we put together showing the finger joining, microwave curing, and inline bending check associated with longer finger jointed individual laminations that are included with long glulam beams. Here's a pre-adhesive layup. There's a couple pictures showing the dry layup of glulam. Couple more pictures showing the face bonding step during the glulam manufacture. Couple more pictures. In this case, we're showing the clamping and curing stage of glulam manufacture. And closing out with a couple of pictures showing the scale of the manufacturing that goes on of the products and finished products, and you know, as they're being milled into their finished sizes. Now on to some projects. Here, these are some pictures from a church in Louisville, Kentucky, and showing some of the very large sizes that were provided on that project and during their erection at the church. The elements themselves were 12¼ inches by 12¼ inches wide by 84 inches deep, and they provided for a clear span of 140 feet for the roof. So very, very large. Another project that incorporated glulam is the Bullitt Center. Bullitt Center is a 6-story heavy timber building completed on May 24th, 2013 in Seattle. It's claimed to be the world's most energy efficient commercial building when complete and achieves the highest benchmark of building sustainability. the Living Building Challenge, or LBC. The challenge is performance-based and evaluated after 1 year of building occupancy. It consists of 20 imperatives, including 100% of energy demands met with on-site renewable energy generation, 100% of water needs met by on-site rainwater collection, on-site waste management, operational windows and natural daylighting in all occupied spaces, and non-toxic, locally sourced construction materials. The project has been designed to last for 250 years. These are a few more pictures of the Bullitt Center during construction in Seattle. The structure itself consists of glulam beams and columns with NLT, nail-laminated timber, used for the floors and the roof. If any of you have had the opportunity to fly through the Raleigh-Durham Airport in North Carolina, if you had an opportunity to look up, you noticed that there was a lot of mass timber. And the Raleigh Airport is the largest glulam project in North America by volume of glulam used. Also, it used a proprietary connection between the glulam and steel. For that reason, the state of North Carolina Building Code Officials Association required it to be evaluated by full-scale testing at North Carolina State University. Here's an iconic project that involves glue-laminated timber. In Oakland, California, the Roman Catholic Diocese commissioned the first cathedral built in the 21st century, the Cathedral of Christ the Light. The building was completed in 2008. The structure is an inverted, double-hulled timber arch sitting on a concrete base. The skeleton consists of 26 vertically arching dug fir glulam ribs, vaulting 108 feet high and supporting glulam louvers. There is a secondary timber structure outside of that, which is clad in glass. If you can remember the Bullitt Center, which was designed for 250 years of life, the design life of this structure is 300 years, because the Archdiocese wanted a structure that would remain standing when everything else is gone. They wanted something that would define the area in which the era in which it was built, and tell future generations about the 21st century. This product is located in one of the highest seismic region and was designed to withstand a 1 in a millennium earthquake. Sophisticated natural daylighting and convection systems were employed as major design elements and led to the name Cathedral of Christ the Light. While timber is often more economical choice for conventional and stick frame structure, you wouldn't imagine the same could be said for the wood system used on this iconic structure. However, the use of timber proved to be a pivotal economic advantage that actually won Skidmore, Owings & Merrill the design contract. The 21,000 square foot structure cost $80 million to build. The strength of the structure is achieved through glulam and pretension steel rod space frames. To give you an idea of the scale, the glulam ribs are 10 3/4 inches wide and 19.5 to 30 inches deep. The louvers that continue to tribute to the dynamic light filtering experience are 5 1/8 inches wide and 22.5 to 39 inches wide. The roof is a tension-free glass oculus supported by a steel tension ring. Western Wood Structures was the glulam system supplier, and they are a great example of the sophisticated wood system manufacturers available in today's market. They were both the supplier and the erector and were able to develop an ingenious way to pretension the steel rods so that the tension on one rod wouldn't affect the tension in another. Now, stepping down in scale. The use of mass timber elements in tall structures here in the U.S. has essentially lagged the rest of the world. Limited by the heavy timber or type 4 type of construction within the IBC, the building code limitations in up to the 2018 IBC. The heights and stories are limited to those below the high-rise thresholds. This picture, this is an example. It's a fire station located in Multnomah County, Oregon. If you look through the glass apparatus doors, you'll notice that you can see the columns, the glulam columns for the frame off on the side there. Another picture on a project. These are some pictures from a recently completed project in Denver using glulam. The 5-story plat 15 structure utilizes an exposed mass timber frame using glue-laminated timber beams and columns supporting CLT floors and roof panels. Now another poll question. We're bringing them at you fast and furious.
Okay, we'll launch this poll. And the question is, what standard spells out the grade mark requirements for structural glued laminated timber? And the answers, the options are A, that's DOC PS 20, B, ANSI APA A190.1, C, ASTM D3737, or D, all of the above. And remember, we're talking about structural glued laminated timber. Okay, we'll go ahead and close the poll. And I'll share the answers or the choices people made. What standard spells out the grade mark requirement for structural glued laminated timber? 7% chose A, DOCS PS 20. 57% chose ANSI APA A190.1. 6% chose ASTM D3737, and 30% chose all of the above. Okay, Jim, let's hand it back to you.
The correct answer on this one is B. The grade mark requirements for structural glue laminate timber is found in A190.1. Folks are paying attention. Thank you for that. Next on the list, mechanically laminated timber. It's another of the elements on the list of those materials that can be a fit for mass timber. You've heard me say this, each time I bring it up, but the key thing is when they are of large enough dimensions and mass. Common names for these are nail-laminated timber and a newer innovation, which is dowel-laminated timber. I'll get you a little bit more information on that in the next few slides. This is a graphic that we put up here to give you an idea on what NLT or mechanically laminated timber really amounts to, and it shows how the NLT is built up and mechanically stitched together. The IBC refers to this method of construction as mechanically laminated timber, and because nails are the older or more common way of providing the mechanical connections, the code provides prescriptive nailing patterns. Also, don't forget that to be mass timber, the members being laminated must meet the minimum sizes spelled out in 603.4 and 2304.11 of the IBC. Speaking about that my reference to being an older provision, here's some information. These are some of the detailed provisions for NLT that have been in the code for at least 50 years. Here's an example that is an excerpt from the 1967 edition of the Uniform Building Code. Shows you a lot of the information, some of the nailing requirements, the sizes, all that kind of good information. And when you look forward in time, you compare that information to the information that's in the that's currently in the code. It speaks to how similar they are. This is the section in the 2018 IBC that speaks to the detailed layup and connection provisions on how to stitch together the NLT together, or how to stitch the NLT together so as to work as a single member. Remember, NLT must have a wood structural panel installed on top to achieve diaphragm performance. Also, when being used as heavy timber floor or roof, Chapter 6 and 602.4.6.1, which refers to floors, and 602.4.7, which refers to roofs, calls for the wood structural panel topping as it helps reduce the probability of a flame-through at any gaps that may exist due to the natural features in the individual wood members. Because mechanically laminated timber, like NLT, is typically made up of sawn lumber, Chapter 4 in the NDS is where you'll find design provisions that are used in conjunction with the Chapter 12 provisions dealing with dowel-type fasteners or nails. Those together, Chapter 4 and Chapter 12, is what is typically used when you're designing nail-laminated timber. When you're in the NDS supplement, of course, you'll see that all of that information is included in Chapter 4 of the NDS. Nail laminated timber. When you're dealing with nail laminated timber, one of the things that comes to the forefront is the ease of construction and prefabrication are a few reasons why NLT is making a comeback. The prefabrication saves a lot of time and money as it shortens the construction time on sites. There is less noise, and from a sustainable aspect, there is less job site waste. These are just a few pictures. The picture over on the left is showing you a jig that was used for the nailing of this particular panel. Shows you some of the erection and what those panels may look like when they're installed. This picture provides a feel for the finished interior of an exposed nail laminated timber ceiling at the roof when it's used as an exposed roof deck. Here's another picture from a project utilizing nail laminated timber and inverted king posts to provide additional strength and a longer span of the NLT. This is a project that's in Culver City, California. It's the Warner Drive project, and it provides some details of the NLT floors while under construction. In this case, the nail laminated timber consisted of 2x12s installed vertically and then stitched together with nails. They used, for the design, they used the NDS principles of mechanics. Another project that used those king posts, this is a project that was completed in October of 2011. It's the Samuel Brighouse Elementary School, School District number 38. It's in Richmond, British Columbia, Canada. It's a 2-story elementary school. It's 50,000 square feet of glulam posts and beam structure. The 10,000 square foot undulating roof was constructed of nail laminated lumber and inverted king posts to span the 35-foot wide atrium. The roof was entirely prefabricated in sections in the shop using jigs to simulate the arched support beams. The resulting warped panels, 40 in number, were then coated, trucked to the site, and erected by the crews. Here's a project that I had the ability to visit while under construction. It's the T3, Heinz T3 project in Minneapolis. I was provided a guided tour with Mr. David Spellman. He's the Heinz VP of Construction, and he provided the tour to myself and Ms. Denise Sandberg. Denise was the head of the Minneapolis inspection unit who was responsible for the project. Project was, as you can see, it was glued and nail laminated timber. The frame was glulams, and then on top of that were the nail laminated timber floors and roofs. It was engineered with the NDS principles of mechanics. Seven stories total, 6 stories type 4 construction, and 1 story of a Type 1A podium. The project was designed to comply using IBC Section 510 of the code. With the resurgence of nail laminated timber, an NLT handbook has been made available. We've included the link over there on the at the bottom of the screen. So if you want to take the opportunity to get a copy of that, that's available. Provides all aspects of NLT utilized in construction and is free for download. Here we have that newer element. We've got a picture here of dowel laminated timber. And this is a dowel laminated timber panel with an acoustic profile integrated into the exposed surface. Dowel laminated timber, or DLT panels, are a next generation mass timber product commonly used in Europe. Panels are made from softwood lumber boards, 2x4s, 2x6s, 2x8s, etc., stacked like the boards of NLT and friction fit together with dowels rather than mechanically stitched with nails. Typically, the dowels are made from hardwood lumber. The dowels hold each board side by side, similar to how nails work in an NLT panel. And the friction fit lends some dimensional stability to the panel. There isn't a prescriptive code path for the use of DLT under the current IBC, and the NDS doesn't provide published design values or equations for calculating capacities of wood dowel joints. To calculate capacities, the Timber Framers Guild provides some good information. However, because nothing is referenced in the code, the use of DLT would require approval by the authority having jurisdiction on a case-by-case basis. Among the advantages of DLT are acoustics. Acoustic strips can be integrated directly into the bottom surface of a panel. This can help a designer achieve acoustic objectives while keeping the wood exposed and allowing for a wide variety of surface finishes. With growing interest in DLT, continued product innovation is likely, along with increased availability by U.S. building designers. Here's a picture of dowel laminated timber. I had the opportunity to actually see this building while it was under construction. It's from the 111 East Grand project, located adjacent to the river in downtown Des Moines, Iowa. The project is only 2 blocks from the office of the Des Moines Building Department. It's not a tall wood project. The building officials from the city of Des Moines reached out to me early on to come in and do a presentation for them, as this was the first new building that they were going to be exposed to. So I did a presentation for them to help them understand and realize the types of information that they need to focus on when doing their plan review and also when doing their inspections. Building officials from the City of Des Moines Permit and Development Center indicate the project is a 4-story Type 3B office building, and it meets all the building code limits for height, stories, and areas that were in effect at the time of their approvals. This shows the DLT floor being supported by glue laminated timber beams and columns. This is just a picture, a finished picture of the finished product, the finished building. It was sent to AWC. It was sent to me by Brian Bishop, one of the, I think he's the deputy director with the City of Des Moines Permit and Development Center. This is just a reprint from the first page of the ICCES evaluation report, ESR 4069, on the DLT manufactured by StructureCraft. StructureCraft were the manufacturers of the DLT used on the project in Des Moines. And here we go with another poll question. Michelle?
Okay, we'll launch the poll. Poll number 4. Which project did not use nail-laminated timber as a building element? A. Samuel Bright House Elementary School in Richmond, BC. B. Cathedral of Christ the Light in Oakland, California. C. Heinz T3 in Minneapolis, Minnesota, and D. Warner Drive, Culver City, California. Looks like a lot of people are paying attention.
Yeah, this one was a little bit different too.
Little tricky.
Yeah, just a little bit. But at least people are staying awake. Those that are that jumped on right after the lunch hour. It's always a challenge.
Right.
Keep folks from nodding off. So I'm glad they're paying attention.
Okay, we'll give a few more seconds. We're pulling for you. Okay, we're going to go ahead and close the poll, share it with the audience. Which project did not use nail-laminated timber as a building element? 4% said A, Samuel Bright House Elementary School. 70% said Cathedral of Christ the Light. 11% said Heinz T3, and 16% said Warner Drive. And the answer is?
The majority rules again. This one was, when Michelle and I were kind of talking about it being a little bit trickier, was because in this case you actually needed to be keeping track of the project names when I was showing all the slides. So good job by those of you that were able to get that one. Correct answer is B, the Cathedral of Christ the Light in church in Oakland, California. They did not use CL or an NLT. Next on the list of those materials that can be a fit for mass timber is structural composite lumber. Effectively, any of the minimally sized SCL elements that are massive enough to be classified as in compliance with the minimum size requirements spelled out in Chapter 6 of the IBC for Type 4 heavy timber construction. LVL, PSL, LSL, and OSL all fall under the structural composite lumber name and definition, as currently referenced within IBC section 602.4. With this slide, what I've tried to do is kind of give you a visual of what these different elements look like. Structural composite lumber is a family of engineered wood products created by layering dried and graded wood veneers, strands, or flakes with waterproof adhesive into blocks of material known as billets. Those are subsequently milled into specific sizes. Structural composite lumber, which includes laminated veneer lumber, or LVL, parallel strand lumber, PSL, laminated strand lumber, LSL, and oriented strand lumber, OSL. They're all permitted for use within the IBC. Here I'm showing laminated veneer lumber for this example. The LVL is produced by bonding thin wood veneers together in a large bullet. The grain of all veneers is parallel to the long direction. The LVL billet is then sawn to the desired dimensions depending upon the construction application. As you can see from the slide, we've got listed some of the common thicknesses, some of the common depths, and that the availability and lengths of up to 60 feet. In order to be used, code acceptance, IBC section 2303.1.10 is for structural composite lumber, and that indicates that ASTM D5456 is the standard that SCL must comply with when used for projects falling under the International Building Code. Moving on, we get to Chapter 8 is where you'll find the structural composite lumber design provisions in the NDS. Some of the features when we get into SCL include its strength when face or edge loaded, and the fact that it's being milled or sawn to consistent sizes. APA publishes some strength properties You're also advised to refer to the manufacturer for more detailed and specific criteria. The general information provided by APA in a lot of cases, you know, the individual manufacturers have more accurate data, specific data that you can use when using their products. And just like that, we're going to throw another poll question at you.
Okay, let's see. We are on the next poll, which is poll number 5. And here we go. Which of the following materials is categorized as structural composite lumber? And the answer options are A, GLT, B, CLT, C, NLT, and D, LVL. From
Just
the first,
some of the alphabet soup that's out there.
yeah. Okay, we'll go ahead and close the poll and we'll share it. Which of the following materials is categorized as structural composite lumber? 8% said GLT, 11% said CLT, 3% said NLT, and looks like we have a clear winner. 78% said LVL.
And yes, they are. They are correct. The correct answer is D. LVL is one of the structural composite lumber materials. Good job. Good job. Last on our list of the materials, those materials that can be a fit are cross-laminated timber, or CLT, and mass plywood panels, or MPP. Cross-laminated timber, if you take a look, you know, the diagram over in the far left, you can see that cross-laminated timber is manufactured by laying up kiln-dried sawn boards or structural composite lumber in layers that are perpendicular to each other. So the one lamination is in one direction, the next lamination is 90 degrees to that. And they are then put together and glued. Each billet of solid wood can be from 4 to 18 inches in thickness and up to 11 feet in width and up to 65 feet in length. Exact sizes will vary by manufacturer and project. The resulting panel of wood is dimensionally stable in plane because there is parallel to grain lumber resisting shrinkage in both panel directions. Now we're up to the standard. PRG 320 is the standard used for the manufacture and identification of cross-laminated timber. And you find that called out in IBC section 2303.1.4. Just a little segue or a little teaser for the future. There's going to be good information in there about the significance in our future webinars, the significance of PRG 320 when it came to some of the final code provisions that were put into place to allow for the taller mass timber buildings that you'll find in the 2021 editions of the IBC. So watch for that and the significance of the newer edition of PRG 320 rather than the version that's shown here and referenced within the 2018 IBC. As we move into the NDS, you'll go down the list and you'll notice that Chapter 10 is the chapter that's designated for cross-laminated timber. Chapter 10 is where you'll find all of the design criteria for cross-laminated timber in the NDS. I thought, you know, as this pops up, I thought I would be remiss if I didn't include a little history of cross-laminated timber. To kind of give you a perspective about, you know, how long CLT has been out there in the marketplace. And also to kind of give you an idea, you know, if you think about the extent of building codes and construction codes, you know, when you start considering that, you know, the building codes have been around for quite some time, and then you compare that to the start date for the patent, 1985, you can see that, you know, it's really within the context of the built environment, it's a fairly short period of time. So in 1985, the first CLT patent took place, and that was in France. In 1993, we had the first CLT projects, which were in Switzerland and Germany. In the years 1995 and 96, that's where some advances were taking place. They had some improved press technology, which, of course, you know, once you start improving upon and start thinking about the technological advances in the manufacturing process, more and more of the product were coming out in a consistent manner and faster. In 1998, we had the first multi-story residential building in Austria. And then in the early 2000s, we had a number of things happen. CLT use in Europe increased significantly. The green building movement pretty much drove that. Better efficiencies, both including the product approvals, improved marketing, and distribution channels were taking place. And over 500 CLT buildings were erected in England. Talking about now, you know, at the present time, U.S. and Canadian use of CLT is starting to ramp up. There's a number of projects that are out there. You'll learn more about those in the future webinars, but there's a good use of the CLT products as they become more economical and more manufacturers are in the marketplace. Shrinkage, you know, so this gives you kind of a couple of photos or a few photos of the CLT press and assembly line. Shrinkage through the thickness of the panel is minimized because the boards are kiln dried before they are laminated with glue and pressure. These are just a couple more pictures that I've got up there showing the CLT manufacturing process. Gives you a sense of scale associated with the elements. Here's some more slides showing the manufacturing process. Some of the steps in the process using glue and pressure to basically activate the pressures used to activate the adhesives. Panels are designed, milled, and shipped to fit together at the site, minimizing any need for site modifications and job site waste. This shows you a number of panels that are ready to be sent out. This slide of graphics I put together to show some of the typical connections used for CLT. You know, you'll notice that you've got internal splines, double surface splines, a single surface spline, and half-lapped. A lot of different ways to connect the different panels so that they'll work as one. From a seismic standpoint, this produces more of an ordinary structural system. However, there is research and testing occurring that is developing special seismic designs and special seismic systems for the future. In this slide, I'm trying to provide some kind of some pictures of the typical connectors being installed in the field. As we start moving forward in time, you're going to find that the manufacturers of the connectors are also doing a lot in upgrading or influencing changes in the types of equipment used by the carpenters on the job site. You'll notice in the one case the electric screwdriver used in the center picture there, and also when you start thinking about installing the connections at the laps, the screwdrivers that you'll get are bigger and longer and designed so that the carpenter doesn't have to bend over. So he's able to install the screws while standing up, helping save on wear and tear on the body. Shake table test, here we go. On October 23rd, 2007, a 7-story cross-laminated timber building was tested on the world's largest earthquake shake table at Miki near Kobe in Japan. It was part of the SOFI project. Italy, which is their portion is Evalsa, which is part of CNR, the Italian National Research Council, and Japan were involved. The full-scale shaking table tests on the 7-story CLT building at E-Defense in Miki, Japan. The traditionally detailed CLT structure performed well when subjected to a variety of earthquake histories with full shake table tests. After the testing, the building was dismantled and shipped back to Italy, where it was reassembled and now houses several families. The slide that I have up there gives you the sizes and the dimensions for the project. And as you can see, it was 77 feet tall, a little over 44 feet along the base and 24.5 feet in the other dimension on the base. The wall panels, the various thicknesses of the material are shown on the slide there for you. So if you're trying to get an idea on how this project was put together for testing. Also, where I indicated that it was provided to us, subjected to a variety of earthquake histories. That meant that there were more than one test. This is just one of the shake table tests that I'm going to show you next. After each one of those tests, they evaluated the connections and then reinstalled the new connectors in a slightly different location to run the next test. And with that, what I'm going to try to do is I'm going to show you the video of the shake table tests on that 7-story structure. You'll notice over on the left-hand side, if you can see some of the flashes, but over on the left-hand side at that mid-rail, those are people standing along the rail. So it gives you an idea on the scale and the size of the project. The testing, of course, with the number of tests and the monitoring, the testing produced a great deal of useful data. And you can see some of the collected data includes the significant movement located on if you were located on the upper floor. This is just a camera inside of that upper floor, and the data included the acknowledgement that the stiffness of the panels and the stiffness of the connections mean that there's going to have to be dampening to help lessen the jarring movement shown on that upper level. Like I said, there's a great deal of research that has taken place since 2007, and that research continues. Now for a few projects. Here's a project that is located near me in Fitchburg, Wisconsin, that use CLT. It's a factory project. It's the Promega Feynman Center, located in Fitchburg, Wisconsin. The structural framework includes glulam beams and columns for the main frame and CLT panels for the floor and roof. In Huntsville, Alabama, there's a private Army hotel, a four-story Candlewood Suites hotel at the Redstone Arsenal in Huntsville, Alabama. That was the first in the United States built with cross-laminated timber. It has 92 keyed rooms, which includes studios and suites, 58,000 square feet, 97 bathrooms, 1,557 CLT panels, 10 beams and 17 columns, and more than 200,000 fasteners, ranging from nails to screws. The typical floor panel was 8 feet by 50 feet and 7 inches in thickness and weighed about 8,000 pounds. The stairwell walls are 37.5 feet tall and weigh 3,626 pounds. In November 2018, Lend-Lease celebrated completing its second mid-rise CLT hotel, another Candlewood Suites hotel, in the U.S. at Fort Drum in Watertown, New York. Upcoming projects include a 5-story hotel in Washington, 2 5-story hotels in South Carolina, and 2 6-story hotels in North Carolina. The volume of wood products used, to give you a little bit more information. There are 935,696 board feet equivalent U.S. and Canadian forest grows, a Canadian forest grows this much wood in 5 minutes. Carbon stored in the wood, 1,276 metric tons of CO2. Avoided greenhouse gas emissions, 494 metric tons of CO2. A total potential carbon benefit, 1,770 metric tons of CO2. 374 cars off the road for a year. The energy saved would be the energy needed to operate 187 homes for a year. So a lot of good information is out there on these projects. And one of the reasons why Lend-Lease decided to go with, they were completely sold on the use of CLT for these series of buildings, these series of hotels that they built. I think, didn't have that. Another slide that that I had, which looks like we didn't include in this, is information about the, or it might be coming up at the end here. So I'm gonna go through here. The next series of slides have been put together to mimic a time-lapse video from a webcam on the job site. The CLT, so if you think about all of the size and the information that we provided to you in the last slide, that the CLT took approximately 13 weeks to erect. So it really went up quickly. So this is just going to step you through, give you an idea on just how quickly that erection took place. Here's the slide. Upcoming is the slide that I was thinking of, and this is the information on the CLT and the blast testing. Buildings constructed for the U.S. Department of Defense often have to meet blast resistance requirements to mitigate the potential effects of terrorism. One of the reasons why there are so many of these hotel projects being constructed at the facilities, the U.S. facilities across the U.S., is because the older hotels and residences that were on site couldn't meet some of the blast safety criteria that they felt was necessary. Terrorism is a growing threat for civilian buildings as well as the Department of Defense facilities. But this, the fire resistance, the blast resistance requirements to mitigate the potential effects of terrorism are included in the reference that I have there up on the screen. But the threat necessitates more building designers to incorporate blast resistance into their designs. The emergence of mass timber construction, cross-laminated timber in particular, offers a sustainable building material that's an alternative that can also meet blast resistance criteria in many circumstances. Here's another CLT project. This is it's a school, an elementary school building located in the historic town of Franklin, West Virginia. The new elementary school structure is a 2-story, 46,200 square foot structure designed for 290 students in grades pre-K through 6th. The colonial design of the building reflects the historic character of the surrounding buildings, with red brick walls accented with beige brick soldier courses and coins, white columns at the gabled main entry canopy, and white windows with dividing panes, stone sills, and keystones. The new school is designed and placed on the site to allow for future expansion of up to 8 classrooms. Not only is the Franklin Elementary School the first new school funded by the West Virginia School Building Authority under the design-build methodology of construction, it is also the first school in the United States to be constructed of cross-laminated timber. Fabricated using wood panels, wood planks, stacked at right angles to one another and bonded with structural adhesives. The solid wood CLT panels incorporate the floors, walls, and roof of the new school. The benefits of CLT include exceptional strength, excellent fire resistance, enhanced speed of construction, and energy savings due to its mass and precise factory production, preventing air infiltration. The next slide gives you, this is just some of the pictures. Shows you the finished result, that architectural look that was referred to earlier. You'll note that the U.S. has been behind in utilization of mass timber. However, with the advent of code provisions and manufacturing advances, CLT is finding its way into the construction of more buildings in the U.S. This 2-story elementary school project was constructed of CLT panels, and its assembly and erection time was only 8 weeks. They were able to close out the school year, and by the time they started up the new school year over the summer, they had a brand new elementary school. This is a slide of the Arbora building in Quebec, Canada. It's 8 stories tall and has 434 residential condos, townhouses, and rentals. The frame consists of glulam beams and columns with CLT floors and roof. Brock Commons, this is the project that is currently the tallest wood structure in North America. The building includes 17 stories of cross-laminated timber supported on glue-laminated timber columns. They did not use beams. They took advantage of the cross-laminated timber's two-way strength on this project. It sits atop a concrete base with 2 18-story concrete cores containing exits and elevators. The podium level is wrapped with curtain wall glazing and glass spandrel panels. An extensive cross-laminated timber CLT canopy runs the length of the building, which is a gross area of 162,700 square feet. In this slide, what I've got here are just some of the tallest buildings as they progress through the years, starting with the Bridport House project in the UK, the Wood Innovation and Design Center in British Columbia, Canada, the Seni di Cambiamento in Milan, Italy, Forte in Melbourne, Austria, 10-story project, the Treat project in Bergen, Norway, which is 14 stories, and the previously referred to Brock Commons project, 18 stories, current record holder, and that's located in Canada. The newest of the mass timber products, this is mass plywood panels. It's a structural composite lumber-based panel consisting of multiple layers of plywood sheathing that are glued together. Like CLT, for code compliance, mass plywood panels are to be manufactured and identified in accordance with ANSI a.k.a. PRG 320. Got a couple more slides that show the mass plywood panels. These are, while under manufacture, these are courtesy of Frere's Lumber. Poll question number 6. Mel.
Okay, let's see. Let's launch this poll. In what country was CLT first patented? A, Austria, B, France, C, Germany, and D, Switzerland. We still have some good participation in these polls. That's great. Okay, we'll go ahead and close the poll and share. In what country was CLT first patented? And 13% said Austria, 59% said France, 17% said Germany, and 11% said Switzerland. So I'll go ahead and hide the results and take it from here.
Yeah, the correct answer is France. Answer B. That was the country where CLT was first patented. Now we're gonna close out with what's going to be a pretty quick session, and that's going to be the concepts of fire resistance design. Then we'll be able to get to questions. Last on the agenda, and the 2018 IBC refers users to the 2018 NDS for the fire resistance design of exposed wood timber elements. That reference to the NDS can be found in IBC section 722.1. That points you, 722.1 points you to chapter 16 of the NDS. And chapter 16 is where you'll find the fire resistance design criteria for mass timber wood elements. What I'm going to do in this is going to be the last slide before we get to the questions. So it's going to provide you with a little bit of information for calculating the fire resistance of exposed wood members. 722.1 of the IBC for the code text points users to the NDS. IBC section 722.6, you'll find that also back in the IBC, but that's for built-up assemblies. That's not for the design of mass timber. Mass timber, you go directly to chapter 16 of the NDS. These are just a couple of illustrations that graphically show how wood elements self-protect against fire exposure. That self-protection is what provides its fire resistance and how it can be designed to structurally perform when subjected to fire. Although far more complicated in actual design, to simplify, the wood chars at approximately 1.5 inches per hour. So for the beam on the diagram on the left to be designed for 2 hours of fire resistance, the size of the beam, the required size of the beam is first determined by the design size needed to carry the load. The beam would then be increased in width by about 6 inches, or 3 inches on each side. The 3 inches is 1.5 times the 2, the 1.5 inches times the 2 hours. And its depth increased by about 3 inches due to the charring on the bottom only. When you're dealing with a column type situation, where fire exposure is on all sides, the column, it's in that size, the size is first determined by the size needed, by the design size needed to carry the load. The column would then be increased in both its width and depth by about 6 inches, 3 inches on each of the column's 4 sides. That's basically it for the introduction to fire resistance. Far more details and information are provided in the future webinars in the series, so please join us for the future. And do we even want to do the last poll question, or do we want to get to regular questions?
It's up to you. We can launch it, or you can show the answer if you want, and we can skip it. How's that?
Yeah, why don't we do this? The question was basically, you caught it, and it's what chapter of the NDS do you find that fire design of wood members? And of course, you have 16 total chapters, and the 16th or final chapter is the one where you will find all of the NDS design information for exposed wood.
Jim, maybe you can speak on the publication that is a really helpful resource for those interested in more information.
Yeah, in addition to the series of webinars that we put together with in cooperation with ICC, we also worked with ICC to create a publication, which we've got up on the screen here for you. ICC is making it available, but the publication is titled Mass Timber Buildings in the IBC. Now, the publication itself goes into far greater detail than any of the webinars that were put together in the series. So it'd be a great resource for you, as are almost all, or I think all of the ICC publications when it comes to helpful hints and tips and information is where you can find information, whether you're dealing with chapters 1 and 2 on administration and definitions, or you want to know a lot of the detail on the new types of construction. It's all included in this publication. So a really good resource for those of you that think you're going to start getting more and more into the use of mass timber in your building construction.
awc.org, which is shown here. There's a quick link here that goes to our webpage, Tall Mass Timber. And maybe, Jim, you could speak on this webpage. And
yeah, this web page we've had up. It's been in existence since before the tall mass timber provisions. Those of you that have been involved with the code development process of the IBC, you can recall seeing this in earlier iterations, and it had all kinds of information that led up to the final approval of the 14 tall mass timber provisions that were approved in Group A, and then the additional tall mass timber provisions that were approved in Group B. All of them are spelled out here. We've got fire test information over on the right-hand side there. So there's a lot of good information there if you want to get into the nitty-gritty of these of tall mass timber. And we've got a link there to some of the mass timber courses that are out there.
right, and this is a really good snapshot view of the new types of heavy Type 4 construction. That includes Type 4A, Type 4B, and Type 4C, and then Type 4HT, which is no changes, I believe, right, to Type 4 heavy timber.
Yeah, it's
construction.
Type 4HT is what is currently found in the code under Type 4.
Right. And Jim mentioned also e-courses that are available on mass timber. If you're looking for any additional information, these are all free to look at, and you can earn continuing education credit as long as you pass the quiz. Okay, and then one last thing, we have our publications that are shown here. You can get to it from, let me go back to our homepage. Over here, the quick links, go to publications, and a lot of our publications are free for viewing online. Okay, so let's I'll hand it back to you, Jim. In the presentation, I'll make you presenter. Okay, one of the questions we received prior to the webinar, because you had the option of writing in a question that you'd like to ask the presenter. And this one said, can you address the new prescriptive methods and what to look for in plan review and inspections?
Okay, this is it's a good question, and perhaps you know, a question that's basically brought about by the thoughts associated with wood construction and the fact that the current IBC, when you're dealing with a project that's incorporating conventional wood, you know, light frame construction, that you can actually go into the code and find prescriptive requirements on how to go about the design of that type of a building. Those types of prescriptive requirements do not exist within the IBC. So when you're dealing with the IBC, or when you're dealing with mass timber, the AWC doesn't have very many resources relative to a prescriptive design for mass timber elements, nor does the IBC incorporate any prescriptive information along those lines. You'll find a lot of that information, you know, a lot of the information relative to the maximum allowable sizes, those types of things. But as far as the prescriptive design of mass timber and, you know, basically putting it together, you won't find that information in the IBC or any of the AWC resources.
Good. Okay. And then another question came in that wasn't really stated as a question, but I think they're asking about fire testing. It states test results on fire hazard.
Yeah, I'm guessing they're wondering about those fire tests that took place relative to the ICC Tallwood Building Ad Hoc Committee. Those were some of the tests. We had that information when Michelle brought up the AWC Tallwood page. You saw that up on the right-hand side there was the link that would take you to the videos. But we've got that information on our Tallwood Building site on our webpage. Plus, there's good information included within the, I think it's going to be the third presentation. So Michelle's doing the next one. And then when Matt gets into module 3, which is the background and overview, that's the presentation where we actually show what happened with those all of those fire tests. And those fire tests that were conducted at the in the United States at the ATF testing laboratories. The other thing to I think to provide an exclamation point on that information, the testing and the data that was collected from that testing was all geared towards the answering questions that were raised by the IBC Tallwood Building Ad Hoc Committee. The results of those tests are what ultimately led to the Tallwood Building Ad Hoc Committee having the comfort to submit the proposals that ended up in the 2021 edition of the IBC. So they were pretty substantial fires. I don't want to provide too many hints, but boy, if you have an opportunity to watch those videos, they were significant fires that were that happened in 5 different scenarios. So
Right.
very cool stuff.
It is very cool. And what's interesting also is what contributed to those significant fires were the contents of the building and not the structure. It's what the fuel that they used to create the fire and the structure. Sorry, I'm kind of
Absolutely
doing a preview of what.
Yeah. The content itself was, using all kinds of synthetic materials and foam plastics, the types of foams that might be used in mattresses and current furnishings. So it was a significant fire load.
Right, exactly.
For the fire geeks in the crowd, it's impressive to watch. I had the opportunity to actually witness one of the fire tests, and boy, you had to stand back from the windows in the observation room because the radiant heat was so great.
Right. Okay, it looks like we're getting close to quarter of the hour. And do you want to just finish out through your slides? And I think you have a few more slides in your presentation to go through. Is that right?
Not, really all I had was I got the one up on the screen, which is the mass timber series. So I put that together to show folks what was up and when those other modules are going to be presented. But other than that, the references, the resources and things are the same ones that you showed. So
okay,
we don't have to continue on with any more slides.
Okay, so let's just have one more question then, and then we'll wrap it up.
Okay.
And this is kind of a different question, but it says, what would be the minimum size building where this mass timber concept is no longer feasible? And to preface this is, how tall can you go with mass timber? Just that. And
Sure. Yep. One of the things, in the new code, in the 2021 edition of the code, I don't want to take away any of the information that's coming in future webinars, but it's also in the code. You're going to be allowed to build mass timber in the type 4A construction up to 18 stories. So, one of the things, as you might imagine, the taller you go, the more cost effective the use of given materials become. So, you know, that might play into the feasibility, but in reality, you know, the feasibility of a project involves so many different factors. So, you know, it's not just the code provisions or what the NDS provides. You also there's a project in Milwaukee that is potentially going to be the tallest mass timber building. So that the willingness of the municipality to entertain and consider these types of tall mass timber projects will have a great deal to do with feasibility of a project. What are the needs? You know, the needs of the developer, the design experience of the architects and engineers on the project. You know, how comfortable they are with mass timber. And then last but not least, you know, I was a code official for many decades, and folks can sometimes forget that zoning provisions can have a significant impact on restrictions that would make it not as feasible to use mass timber. So way too many factors to suggest that the code and the standards themselves have a great impact on feasibility. The changes to the 2021 code will make it easier, but really that's not the prime driver when it comes to feasibility of different materials on a project.
Right, various factors. Well, thank you very much, Jim, for providing us with a very informative webinar. And I also want to thank Lori Cook, who helped behind the scenes. She's our engineer on staff that's part of the education team that helped out with answering questions that were rolling in throughout the presentation. Thanks, everyone.
Take care, everyone. Thank you.